This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
Good evening. My name is Nigella Hilgarth, and I'm the Executive Director of the Birch Aquarium at Scripps Institution of Oceanography, UC San Diego. And I'm delighted to welcome you all here this evening to the latest in the Jeffrey B. Graham Perspectives on Ocean Science. And it's my great pleasure this evening to introduce our speaker, Dr. Paola Cessi. Paola is a professor at the Physical Oceanography Research Division here at Scripps Institution of Oceanography. And she did her undergraduate work at Bologna University in Italy, and she did her graduate work at MIT. It's a joint program with Woods Hole. But she saw the light, and she came to Scripps and is a professor here. And she specializes in models of the oceanic general circulation, convection in geophysical fluids, and models of climate dynamics. The size and complexity of the oceans present a huge challenge to people who want to mimic the movement of ocean water and to really understand ocean dynamics. And so I'm very excited because tonight she's going to explain how this new age of supercomputers is actually allowing people like Paola, ocean modelers, to actually investigate how the deep ocean water is affected by changes in surface water and by the influx of fresh water as well. So please join me in welcoming Paola for her presentation entitled Modeling Ocean Circulation in the Age of Supercomputers.
Thank you. So this is work that I've done with Christopher Wolfe. He is a postdoc, also at Scripps Institution of Oceanography. And my work is sponsored by the Department of Energy. So here's the outline of what I'm going to talk about. I guess no pointer. So the first thing that I would like to explain is how the ocean and atmosphere heat transport affect the temperature regulation on Earth. Then I'm going to try to convince you that the Atlantic Ocean is very special in the way it transports heat.
There's a pointer there, right? Pardon.
Oh, thank you very much. And then I will explain how we use supercomputers to understand ocean and climate as well, although I'm not going to talk about this very much. And in particular, our little Hobbit model that we use to understand the circulation in the Atlantic Ocean. And in particular, this beast, the pole-to-pole overturning cell, which makes the Atlantic a very special ocean. And then we'll conclude with some remarks on how that circulation can change as the Earth warms up. So the first thing that I'd like to explain is, why are the poles colder? Well, the sun is very far away, so it hits the Earth with parallel beams, and those parallel beams are the same at every latitude. However, because the Earth is a sphere, the area that it hits at the equator, and here is an example of how the sun is at the equinox or in the annual average at the equator. But if you are at 30 degrees north, then even though the sunbeam has the same intensity, it hits the Earth over a larger area. So that same energy is spread over a larger area, and therefore every square inch of the Earth here gets less heat than it did at the equator. If you go further up, here is at 60 degrees, the beam is the same, the energy is the same, but the area hitting the surface of the Earth is larger still, and so every square inch of Earth in high latitudes received less energy per unit area. So this is why, even though the sun really comes parallel to the, at every latitude, once it hits the Earth, you get less sunlight per unit area in high latitudes than you do in low latitudes. So light then is absorbed by the atmosphere, and some of it, and the Earth, surface of the Earth, and some of it is reflected. And here I show a map of the absorbed solar radiation. And the colors, the warm colors indicate more absorption, and the blue colors indicate less absorption. And as you see, there are changes also in longitude, as well, of course, as changes in latitude, because the color of the surface of the Earth varies. Dark colors, such as the ocean, absorb more light and thus gets heated up more. Light colors, like the desert here of Africa, which is just here, gets less heat from the same amount of sunlight that shines next to it. And then near the poles, because it's colder for the reason that I explained you before, there is ice that is formed, and ice is white, and therefore it reflects more light. And so these places that are already colder because they receive less energy by the sun per unit area are even colder because they reflect more sunlight and then gets heated up less. So then you can ask yourself, and this plot just shows the amount of heat absorbed as a function of latitude averaged over all longitudes. Then you might ask yourself, what would happen to the Earth's temperature if the ocean and atmosphere were at rest, if they didn't move? So here is a plot in red of what the temperature averaged along a latitude circle over all longitudes, and also averaged over a year, would look if the ocean and atmosphere were at rest. Near the equator, the temperature would be above 100 degrees Fahrenheit, and at the pole would be below minus 120 degrees Fahrenheit. And you see there's a big jump here in the temperatures as you approach the poles because of this effect of the ice reflecting heat back. Fortunately, the atmosphere and ocean move, and therefore we do not have these extreme differences in temperature of about 250 degrees Fahrenheit between the equator and the pole. We have a much smaller range of temperatures of about 30 degrees centigrade, about 50 degrees Fahrenheit. Notice that San Diego would be a nice place to live either way. So it's very important to understand how the ocean and atmosphere moves because they determine the equator to pole difference. So let's look at the heat transported by the ocean and atmosphere together. This is the blue line. This as a function of latitude. So this is the total heat transported along, again, averaged over the year and integrated over all longitudes as a function of latitude. And it's measured in petawatts. These are 10 to the 15 watts. And because this is plotted as northward transport, it is positive in the northern hemisphere because the heat is transported from the equator towards the pole so that you warm up the poles, but negative in the southern hemisphere. So in fact here the transport is southward. That is again from the equator where it's warm towards the pole where it's cold. So this is exactly why the actual temperature observed on Earth doesn't have such extremes as it would with the atmosphere and ocean at rest, because the ocean and atmosphere together tend to transport heat away from the equator and towards the pole. And surprisingly, the atmosphere transports rather a lot more than the ocean, which is here in red. I say surprisingly because the mass of the atmosphere is much, much less than the mass of the ocean. But the velocities are much bigger in the atmosphere. The velocity of the winds are much bigger than the velocity of currents, and that's why this is so much bigger. So here's the ocean transport. And that's what I'm going to talk about mostly, the ocean transport in the remainder of the talk. And when you look at this, it's also very curious that there is more transport towards the pole, from the equator to the pole in the northern hemisphere, than there is transports from the equator to the south pole in the southern hemisphere. This value is about 2 petawatts. This is about 1.5. It's surprising because, in fact, there's rather more water, more ocean in the southern hemisphere than there is in the northern hemisphere. About 4/3 in the southern hemisphere compared to the northern hemisphere. And yet, the transport towards the pole there is less than the transport in the northern hemisphere. So why is that? And this is where the Atlantic becomes the odd ocean, because now if you partition the ocean heat transport performed by all oceans, this is the black line, again as a function of latitude. So here's again heat transport in petawatts just due to the ocean. The black line is the total transport. The green line is the transport performed by the Pacific Ocean, and the red line is the transport performed by the Indian Ocean. There's no Indian Ocean about north of 15 degrees. It's all land here. That's why this line terminates here. And the very curious thing is that the Atlantic Ocean has northward transport that is positive everywhere. What that means is that it is transporting heat from the equator to the pole in the northern hemisphere, but from the pole to the equator in the southern hemisphere. That's very strange. So the Atlantic is trying to make the equator warmer and the poles colder. Very naughty. So that's why the sum is less in the southern hemisphere than in the northern hemisphere. As a result of this, the South Atlantic is about 2 degrees Fahrenheit on average, if you average over the whole South Atlantic, colder than the North Atlantic. So now the question to understand is, why is the Atlantic so strange? Why does it want to transport heat from the equator to the pole in the northern hemisphere, but from the pole to the equator in the southern hemisphere? And as I will try to show you, this is because it has a big cell going from pole to pole. And the big cell, this is a cartoon of how we try to sort of sketch the circulation in the world ocean. So this is a sketch of the overturning circulation. So I have to spend a little bit of time on this. So there's these arrows and then these colors. Okay, so the arrows obviously show the direction of the flow, and the color shows where it is located in the water column. So the red flow is near the surface, and the blue flow is deep. So, and here is the Atlantic Ocean. So there is a cell that has water flowing at the surface from the southern end of the Atlantic to the northern end of the Atlantic, and then from the northern end to the Atlantic at depth towards the South Atlantic. Now, the water near the surface is warmer than the water at depth, and so the net result is that you transport warm water from the South Pole towards the North Pole, cold water from the North Pole towards the South Pole. So the net result is a transport of heat from the southern hemisphere to the northern hemisphere. Now, it doesn't just occur in such a simple thing, in a simple cell like that, because right here around Antarctica, there are no continents, and you can just flow around in this circumpolar region. I'll show you in a second. And so the water, rather than just going up and down like that, it takes a big detour going all the way around and coming back from this other side of the circumpolar region, and a few detours in these other oceans. I'm not going to talk about those. So, there's one thing that goes on at the same time that I forgot to say. And so you have sinking of water here from the surface towards the depth. And here instead you have upwelling or rising of the water from the depth towards the surface. This is what these little arrows pointing up means. These circles with a dot in the center is like an arrow pointing up towards you. So we're trying to understand why this happens and what drives this pole-to-pole flow in the Atlantic. So here is a somewhat complicated plot. I'll try to explain to you what it is. This is a plot of density across the Atlantic as a function of depth and latitude. Here's the equator, here's the northern Atlantic, and here's the South Atlantic. And these are measurements taken by going with ships along this track from Iceland to Antarctica and dropping instruments in the water that record temperature and salinity. And then from that, you can reconstruct density. And this black forms here is just the ocean bottom. Now, this picture, of course, is not true to the aspect ratio of the ocean. These are 6 kilometers of depth, and here these are 14,000 kilometers of depth. So it's a shallow little tiny thing. We showed it like this, otherwise we wouldn't see anything. So the interesting thing that this plot shows, well, one of the interesting things that it shows, is that actually near the surface, the water, let me just say, the green is denser than the pink water. That's why it's at the bottom. Okay, so here you have light water sitting over denser water. And the interesting thing is that, in fact, in the Southern Ocean, near the surface, the water is denser than in the North Atlantic. But remember that the cell goes this way. So it's going down where the water is relatively light and coming up where the water is relatively dense. That's not what we normally think of, our intuition about how water would go, because if you have dense water, it would go down, and where it's light, it would come up. Well, again, the Atlantic is very strange because it does exactly the opposite. You have water going down here and coming up there, even though it's denser here than it is here. Okay, so how are we going to understand that? So in the ocean, or the atmosphere for that matter, you cannot go out and make an experiment trying to change the wind or change the temperature or change the fresh water or the shape of the ocean. They are what they are. You can just go there and measure them. But if you try to understand how it works, then you have to do an experiment where you can change properties and see how the ocean reacts. And so that's where we can't do this in the Atlantic Ocean. So that's where we resort to experiments using models that then we solve using a computer. So how do you do that? So you take the ocean that you're interested in, and you divide it in boxes like this. And then you solve some mathematical equations which tell you how the water moves when you change the temperature, the salinity, and the winds. And you solve these mathematical equations inside these boxes for as many boxes as you can. So how many boxes do we pick? Okay, well, we have choices. So you can have, for example, you can make a grid for the ocean and the atmosphere for that matter, that has 6 degrees of latitude on each side, and then maybe 20 levels in the vertical. So that's, there's a lot of grids like that, and still, to just give you an idea of what a grid like that looks like, in a grid like that, the temperature, and I've drawn this grid over a map of California. So for that grid, the whole of this Northern California, plus a bit of Oregon and Nevada, all has one temperature. And the same thing for this other grid point, it would have one temperature. It's not very good, but this is what you can start with. Then if you put a finer grid, then this is, for example, 1.5 grid, then you see that you cover, you would cover California with, you would have here 4 by 4, 16 times as many grid points. So it's better. So then the question is, what difference does it make? So here it's a movie of the ocean circulation around Antarctica, for example, done by our colleagues at the Geophysical Fluid Dynamics Laboratory in New Jersey, where they model the speed. I think I do this. Nope. How do I get it to play again? The speed of the currents around Antarctica. Remember, I was telling you things go around in Antarctica. So this is when you have a 1 degrees, that's about 110 kilometers per in the side grid. Now, if you have a 1/6 of the degree grid, that is an 18 kilometers grid, this is how it looks. There's a lot more structure, obviously. You see these vortices that we weren't seeing before. They're not here. And also the velocities, the maximum velocities, are much larger, about a factor of 10 between this calculation and this calculation. So obviously, well, not obviously, actually, it turns out this calculation is more realistic than this. This is more like what the ocean looks like than this. So then you say, well, then why don't you all use a huge number of grid points and have a smaller grids? Well, that's because our computers are somewhat limited. So what kind of a computer does one use to make calculations like this? Here it is. This is what a computer where we do these big calculations looks like. I don't know if you can see it. It's a stack of about 100 cabinets, each about a person tall. And there's, they have a footprint. Well, this is one particular computer. In fact, the second one in the world for speed. It used to be #1 until about October of 2010. And then another computer beat it, and that's in China now. And these numbers change all the time. There'll be another one soon that beats the Chinese one. So, but just to give you a scale, the footprint of this computer is 4,400 square feet. It has 255,000 CPU. This computer has 2, okay? And it uses 4 megawatts per hour. That is about 4,000 hairdryer going on 24 hours a day, 7 days a week. And it costs, this has an electricity bill, never mind what it costed. Its electricity bill is about $3 million a year. And this is in Tennessee, because this is located at Oak Ridge National Laboratory, where the cost of energy is one of the lowest in the country. If it were in California, it would cost $4.5 million a year of electricity. You think they should have put a person here just to give you an idea of the scale, but I guess when they took this photo, this must have been running. And it's so loud, you don't want to be in there when it runs. It's like being inside a jet engine. So this is a very big computer, and this is what you need to do those calculations, and it's difficult to make them much bigger than what a computer like this can take. And this is, you know, this is the number of operation that it does, 1.7 petaflops, which is this many operations per second. Okay, so what does it look to compute on Jaguar? So here's a colleague of mine, I should have written her name, I'm sorry, Julie McLean, also at Scripps, gave me this movie. This is the sea surface height, the height of the ocean in centimeters as a function of latitude and longitude for the world ocean. And this is for a model that actually simulates the ocean, the atmosphere, and the land. And it has an 11-kilometer grid, and it takes about 2.5 days of computing time to simulate 1 year. So you can see that if you want to predict the future and you want to simulate 20 to 50 years, it takes many, 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 many days to do a calculation like this. And obviously those supercomputers are used not just by oceanographers and atmospheric scientists, they're also used by other type of scientists, biologists, nuclear physicists. So it's just not possible to do very many calculations with a model like this. So are things going to improve? Will we be able to make bigger calculations? I think so for the next 40 or 50 years. This is a plot of the number of operations per second flops in logarithmic scale. So each of these is 1,000 times bigger than the previous scale as a function of time. This was in 1950. This is 2010. Here is Jaguar, the computer that I showed you a picture of before. And it looks like every 15 years you get a speed up of about 1,000 times. It's a lot. It's not obviously going to continue forever, but for the next foreseeable future, it will continue as done so for the last 50 years. So yes, we will get bigger computers, we'll make more refined models, and I think our answers will be better. So, but we wanted to do calculations where we changed a lot of different things. So we didn't do a model of the global ocean, as we call it. We just did a model of the Atlantic Ocean only. And we simplified certainly the geometry. We decided, well, in order to understand how this pole-to-pole cell works, I'm not going to worry about the complications of the coastlines or the bottom floor of the ocean. And I will just model the Atlantic Ocean as a shoebox. A big one, although not as big as the Atlantic, is about half as deep, half as long, and half as wide in the North Atlantic. Sorry, as the full Atlantic. This is Northern Hemisphere, this is Southern Hemisphere. But we think it was very important to have that circumpolar region that goes all around Antarctica, where the flow can just go around. So how do you make the flow go around in a geometry like this? Well, you take whatever comes out of this opening here, and you put it immediately back there. That mimics the fact that the current can flow around Antarctica and come back to the same place. Okay? So here there's a wall the flow cannot go through. Here there's a wall the flow cannot go through. But here the flow can go through. And where does it go? It comes back on the other side. That's the special thing about the circumpolar current. Let me see if I can go back and show you the movie again. Oops, there it was. So you see, that's what we're trying to mimic, is the water goes around here. And here's the Atlantic. It comes out of Drake Passage. That's the name of this opening here. It goes all around and then comes back through Africa again. Okay, so that's what we are trying to mimic. Okay. So we prescribe some winds that blows on the surface of this box, which is filled with water. Okay, I didn't show you here the water because I wanted to show you the shape of the box, but it's filled with water. and when we blow wind over it and we heat up near the equator and cool down at the other two ends. And this is how the temperature at the surface looks like, for example, just looking from above, and it's cold near the poles and warm near the equator, but you see there's all this motion that is shaping the temperature distribution. You see waves here flowing by, all these crenellations. And here is the sea surface temperature, which tells you how the velocity is. And so let me see if I can run it again. Nope. So if you follow these lines, that's how the velocity looks like. And you go around in this direction when it's red, and in this direction where it's blue. And there's these large currents here. You go straight through here, coming back every time. And then these crenellations are just these little vortices that you can capture when you have 16 million points to represent this ocean. Okay, so this is just a surface, the sea surface height as a function of longitude and latitude here. Okay. Okay, now we started to look at the overturning circulation. So the beauty of this simple model is you can now change things. And one thing that we changed was the shape of the box. So what happens if Drake Passage, that opening that we have in the circumpolar region, was closed? And you no longer have a circumpolar region where fluid can get out and come back in. It just is confined on all 5 sides by a closed box. So what I'm showing here is 2 things. In colors, I show the sense of circulation, what we call the overturning circulation. And deep colors means that it's stronger. And when it's red, it means it is flowing like this. And when it's blue, it means that it's flowing like this. And then in gray are the temperature lines, isotherms we call them, lines of constant temperature, as a function of depth and latitude. And here's the northern hemisphere, here's the southern hemisphere, here's the northern hemisphere, here's the southern hemisphere. And we have the wind is the same in both calculations. The temperature distribution at the surface is the same. The only thing that is different is that we close the box. And what happens when you close the box is that this pole-to-pole circulation, which was sinking in the northern part of the basin and rising in the southern part of the basin, actually pretty much is gone. And in fact, if anything, you have flow going the other way. So there are some differences in the temperature, but those are perhaps not very important, except to say that here, I don't know if you can see these gray lines in this blue background, but actually there aren't any down here. So although there is a circulation here in this direction, it is occurring at temperatures that are all of the same value, and so there actually is no heat transport in this circulation. This is, of course, more realistic, like what we have. So now one thing we understand, so first of all, from this experiment, is that it is very important to have a circumpolar region in order to obtain this pole-to-pole circulation, which characterizes the heat transport in the Atlantic. If you close Drake Passage, that pole-to-pole circulation disappears. So this is a sketch of what is going on, and it's pretty complicated, but I'll try to explain what is going on. So again, here is depth, and here is latitude. The equator is at the center, the North Pole is to the right, the South Pole is to the left. And these lines here are density or temperature surfaces. Okay. And what is important about having this notched region, this circumpolar region, is that the action of the wind, when there are no boundaries, generates a circulation in the ocean which is like this, where there is suction, water coming up due to the wind and going down outside of the notched region. So there's a circulation like this. Even though the wind in the northern hemisphere is the same as what it is here, because of the walls on the two sides of the box, the net result of the circulation is the opposite. It actually goes down in high latitudes and up in low latitudes, and also is much shallower. So then the wind pushes the water in this direction here and this direction here, and now you have these temperature surfaces that are the same in the northern hemisphere here as they are in the circumpolar region. And these represent some freeways along which the flow can go very easily and therefore connect these two cells in a pole-to-pole cell such as this. Okay, and what happens in the middle is not so important as it happens. So if you have this geometry and cooling here and heating here, you can have this circulation. When you close the circumpolar region by making it a closed box, then these two cells, due to the wind, well, this stays the same, but this one reverses. Okay, this one reverses, and so you cannot have a pole-to-pole cell. There is no way you can construct a pole-to-pole cell in this region because the water is going the wrong way here. You do have something very weak here, but that's not very important. Okay, so that was one experiment we did, or rather two experiments we did. And then we did an experiment trying to understand what would happen if the northern hemisphere warmed up in high latitudes. So this is the same calculation as before. We have this pole-to-pole cell here. And then we did another calculation where we warmed or added a little bit of fresh water. It's the same thing, really. In the northern part of the ocean. And this circulation, once again, collapses, goes away, disappears. And why is that? The reason is that when we warmed up this region, we closed this lane of freeways that was open between the northern part of the ocean and the circumpolar region. There are no more density surfaces shared between the surface of the circumpolar region and the northern high latitudes. They're gone. So even though there are these cells due to the wind, they're still present. There's no way to connect them. There's no freeway, and the circulation disappears. Conversely, if you warm up or freshen, adding light fresh water in the southern hemisphere instead of the northern hemisphere, you open up more lanes of this freeway and the pole-to-pole circulation would increase. Okay. So when we look at warming the high latitudes, which we know will happen, is happening actually as we warm the planet, it turns out that the high latitudes warm up more than the equator. Depending on whether we will melt more ice and increase the temperature in the northern hemisphere, that was the previous scenario, or if we melt ice and or warm in the southern hemisphere, the pole-to-pole cell might increase or decrease. So I think at the moment, the odds are that the scenario will be like this, because the prediction is that the northern hemisphere will warm up more than the southern hemisphere. So we actually expect the pole-to-pole circulation to collapse and not to increase. Certainly Hollywood, I think, has decided what they think is going to happen. So this was the day after tomorrow. A not very good movie. I don't think I have. Yeah, thank you. So this was the day after tomorrow. A not very good movie about what happens when the thermohaline circulation collapses. And as you can see, they think that New York City will be completely under ice. I don't think it will be quite like that. But certainly the implications of the thermohaline collapsing, the overturning circulation, the Atlantic overturning circulation collapsing are very scary and far-reaching. So we're still trying to understand that. So let me conclude, and while I conclude, let me just show you a characterization of what happens to particles, how the particles move in our models. Because I've shown you these sketches, and it seems like the overturning circulation is such a smooth cell going around. But actually, if you look at particles, how they move, they're very complicated. So you just have to follow these particles going around, and then they have little tails. And here it is. Here you see that when they enter the circumpolar region, they go around, and then they come back. They go out of here and back in here. So the real motion is very complicated, and I don't understand it too well myself. But just to show you the complexity of the ocean motion, I thought I would put this up. This is particles as a function of depth here, latitude, and longitudes, trying to give you a three-dimensional view. In fact, this is a two-dimensional screen, so I can't do anything about that. But they come down, and then they go along the western side of the basin, and then they flow around. And then here in the circumpolar region, they just keep going this way, down and up, down and up. So it's very complicated motion. And models, I think, can be useful to understand physical processes in the ocean and in the atmosphere. And it's interesting that the Atlantic overturning depends on many things. It depends how the wind is in the ocean, how the temperature is, and how the fresh water also is at both the northern end of the ocean and the southern end of the ocean. Thank you. Yes. So the question is, what kind of velocity are involved? You mean what is their value?
Water speed.
Yes, the water speed. So typically, the water speeds here near the surface are about 1 centimeters per second. In the Antarctic circumpolar region, they're more like 10 to 50 centimeters per second. And in these boundary currents here, they can reach 1 meter per second. So there's a about 2 orders of magnitude. Of course, there's also smaller velocities. These are the horizontal velocity. The vertical velocity are more like 1 millimeter. They're about 5 orders of magnitude smaller. So to go up and down, it takes a lot less, but also there's a lot less water, a lot less distance to go. Because remember, these are only 2 kilometers, and this is almost 10,000 kilometers. So even though the velocities in the vertical are smaller, they get up and down at the same speed as these take to go north to south, approximately. So the question is, how does the the Atlantic overturn affect nutrients and primary production? So where you have upwelling, usually you bring nutrients towards the surface, and where you have downwelling is the opposite. So, so the overturn at the moment is making the circumpolar region extremely productive, very much more so than any other places in the ocean. Of course, there's not always sunlight. Sometimes this is covered by ice, so that doesn't help plants. But
and just as a clarification, is the Gulf Stream a part of this Atlantic overturn?
That's a very good question. It depends. Okay. Yes or no? Okay. So the Gulf Stream proper is a current. First of all, this is not, the Gulf Stream proper is not really captured in this particle moving calculation, because all the particles were placed below a certain level, whereas the Gulf Stream is occurring at a higher level. So this is showing what we call the deep western boundary current. Okay, so the Gulf Stream would be above. So the Gulf Stream moves water near the western boundary here in a swift current that moves towards the north in this region. That's not completely part of the, so strictly speaking, that is the Gulf Stream. So that is not classically a part of the overturning circulation. However, then some of the water deflects from the Gulf Stream proper into a current that sort of crosses the ocean from from southwest towards the northeast, which we call the North Atlantic Current. And that is properly the, actually maybe I have a better picture to show you that, I don't know. Yeah. So the Gulf Stream proper would be a current right along the boundary here, okay? So, and then there's some current, you see this sort of diffuse current here. That's more what is involved in the meridional overturning branch. We call it the North Atlantic Current. So that is more properly and more classically associated with the meridional overturning. Whereas the Gulf Stream would just be this little bit here. So, but you know, in the end, they're all part of the general circulation. So these distinctions, I'm not sure that is what people give names to. Is the Gulf Stream part of the transport of heat that occurs in the northern hemisphere? And the answer is yes. Yes, definitely it is. I'm just looking for the, yes. Yes, so some of this transport is due to this pole-to-pole cell, and some of it is due to currents such as the Gulf Stream transporting heat. So they're all lumped together in this figure. So in some sense, you can estimate from this plot the part that is due to the meridional overturning and the part that, not in a precise way, but so the part that is transporting heat the wrong way in the Southern Ocean is the overturning component. And you see it's bigger here. And so that part is probably due to the Gulf Stream. Yes. So the question is, are there any theories for what effects there will be if the North Atlantic current changes? And the answer is yes, there's many. First of all, because of the transport of heat here decreasing, the climate of the northern hemisphere would become colder, especially the eastern side of the Atlantic, that is northern Europe. And at the same time, we would expect the climate in the southern hemisphere of the Atlantic to be improved. However, there are far-reaching consequences, as I said, because what happens when, okay, so let me go back to this figure. So you see that the atmospheric transport is slightly bigger, slightly smaller in the northern hemisphere than it is in the southern hemisphere. And that, I believe, is in response to the fact that the ocean transport is larger in the northern hemisphere than it is the southern hemisphere. Therefore, as the transport of the ocean changes, we expect the circulation in the atmosphere to change as well. And the atmosphere is not confined by the continental boundaries as much as the ocean is. So the effects of changes in the heat transport in the ocean would be reflected in the atmosphere, and those would be reflected on all around the globe. And you know, there's several studies that show like precipitation in the tropical Pacific changes when you do these model experiments, when you force the meridional overturning circulation to stop or be reduced by putting some freshwater pulse in the northern hemisphere, and then these models, which also has an atmospheric component, they look at what the reaction or the effect of that is, and there's effects everywhere. So your question is, do these calculations give you an idea about the rate of change? And the answer is yes, they do, except we have not done the analysis yet. But absolutely, and that's why we're doing these movies with the little particles, to see how long it takes for changes applied at one end of the circulation to occur in the other end. And the answer is 50 years. 50. Okay, from one end to the end, say you make a change near the North Pole, how long does it take before it's felt in the South Pole? That's 50 years. But for how long it's felt in the Northern Hemisphere, that's much less. I think of the order more like 10 years. The focus is on the Atlantic. Why didn't we look at the Pacific? We did, actually, in the sense that, when I can find it, when we applied this warming or freshwater anomaly at the northern end of the basin, then we put ourselves in the situation which is the current climate in the Pacific. That's how it is in the Pacific at the moment. The Pacific, in fact, does not have a pole-to-pole cell like this, because it's the density in the northern part of the Pacific are lighter than in the Atlantic. And therefore, this connection of density between the northern Pacific and their circumpolar region does not exist at the moment in the present climate. So Earth has already, in some sense, done the experiment for us of what would happen if you warm up or freshen the the northern end of the Atlantic. It's the Pacific. Then you get a circulation like the one we have in the Pacific. The 50-year time scale is how long it takes if you make a change here to be felt down here. Okay, so the Pacific is already in this situation. It's been there for a very long time, so it's just fresher and less dense at the surface. And so you don't have a pole-to-pole cell in the Pacific. Well, many people are working on this problem, and in particular, there's a very large program in cooperation between the United Kingdom and the United States to measure changes in the pole-to-pole overturning by placing instruments at one end of the Atlantic on the US side and the other end of the Atlantic on the United Kingdom side. And by placing instruments at these two ends, and in fact some in the middle as well, they can monitor changes. And this program has been going on for since 2004 now, and they've already seen some changes, but of course small, because it's only been 6 years.
Well, we're just about out of time, but thank you very much, Paula, for a great talk.
Thank you.